Raja sir is not fully visible.
Niraj sir, you can start.
Can I start?
Niraj sir, introduction.
Yeah. So the next lecture of this today's session is by Professor Sebastian. So let me introduce him first. Professor Sebastian obtained PhD degree from Faculty Libre des Sciences de Lille, France in 1979. He has contributed to the development of semi-insulating third and fifth materials, including third nitride for discrete and or integrated device fabrication and buried heterostructure lasers for high-speed data and telecom applications. His current interests are the integration of third and V groove on silicon, high-power buried heterostructure quantum cascade laser, and semiconductor for nonlinear application. Professor Sebastian was a laureate of foundation of the France, Paris in 1978, a team member that won gold food from Technique magazine for the breakthrough in information technology in 1999. He was Sir C.V. Raman visiting professorship lecture at I think it's not visible. Yeah, yeah. I welcome with this brief introduction. I welcome Professor Sebastian to deliver his lecture. Please welcome, sir. Yeah.
Thank you very much. Let's see. Can you see my screen?
Yeah, it's visible.
Okay. So, yeah, I would like to thank you very much for the introduction, and also I would like to thank the organizers, especially Professor Grace, for inviting me to this wonderful seminar, conference by Zoom. We are all suffering from pandemic, but I think it is a nice occasion. We gather together through this very advanced technology, and I'm very happy to be part of this program. So I would like to talk about advanced photonic devices enabled by hydride vapor phase epitaxy. Before I would like to go, probably the one who introduced me didn't tell. Actually, I'm also adjunct professor at VIT, and I really cherish the memory of my stay in 2018. This is the photograph of my students with whom I spent almost a month. So I still cherish the memory of my stay. I would like to start this topic with this figure. Okay, the outline of the talk is I will introduce what is hydride vapor phase epitaxy, and also I will show some device examples what we have achieved. I mean, we cannot achieve everything only by hydride vapor phase epitaxy, but we, as the title says, it is enabled by hydride vapor phase epitaxy. So we have to use also other epitaxial techniques. And I will show some of the device examples. Let me see. Integrated photonic devices, buried heterostructure quantum cascade lasers, and very recently we are working on orientation pattern gallium phosphide for quasi-phase matching. And this, of course, we only a starting stage, so there won't be much results, but I will show some of the results what we have achieved. So what is the need for epitaxial techniques? Of course, probably many of you know, but for some who are not aware, if you take a complicated structure, it always contains several layers. You have to grow on a substrate epitaxially. It has the same crystal structure as a substrate. And for that, we need several epitaxial techniques. There are several epitaxial techniques available, but also not only we are growing only layers on planar substrates, but also sometimes we have to grow some kind of structures like this, you need the basic structure, but at the side you have to etch down, and then you have to grow also at the side. So you have to need a technique which also can grow something on non-planar substrates. I would like to give a very brief introduction to the transport processes, and where all the major epitaxial techniques are kind of control the processes. So if the input amount, what you are putting inside the reactor, is the one which controls the growth, then we say it is thermodynamically controlled. So here is the gases coming in, and they diffuse and they react on the surface. That is where the deposition takes place. And then the unwanted product, they have to out diffuse. So we can say number 1, 2, and 4, and 3, these are some of the processes. And 1 is just input amount. If the whole process is dependent only on the input amount, then we say it is a thermodynamically controlled process. If the process is controlled by diffusion, then we say it is a diffusion control process, and MOVPA operates in that regime. And VPE and LPE operate in thermodynamic regime. And all the surface events, you have adsorption, surface diffusion, site incorporation, desorption of unwanted products, all these, I clump them as surface events. And if everything is fast, only this number 3 is slow, then we say it is kinetically controlled process. And we say, for example, MBE, for example, it is a kinetically controlled process. Okay, this is just to have some kind of background so that you can understand the various processes which are used as epitaxial techniques. So in metal organic vapor phase epitaxy, it basically uses metal organic sources, for example, for 3,5 compounds, metal organic 3 sources, and 5 hydrates, arsine and phosphine or alkyl hydrates. Basically, it is a cold wall reactor, less parasitic reactions. It is a diffusion controlled, low growth rate. So you have the gases are coming in here, and here you have the susceptor where it holds the wafer, and the reaction takes place. The products they go out, the gas. So this is a very robust technique, and this is used largely for all optoelectronic devices today, most of the optoelectronic devices. And we have yet another technique called molecular beam epitaxy. So basically, it is the toy of the physicists because they could grow very low dimensional structures in the beginning. And it is a completely high vacuum, ultra high vacuum technology. You have to have very high vacuum, and you have the sources which are placed in the effusion cells. And since there is a very high vacuum, when you heat the effusion cells and you open the shutter, the beam will evaporate, the molecular beam, they will evaporate and just go strike the wafer here, and all will react. And that is why only the reaction at the substrate is the one which is, dependent. That is why it is called a kinetically controlled process. So again, here you can control the growth rate in very in the monolayer level. And that is why this is also used for very advanced device fabrication. Now, I am going to talk about hydride vapor phase epitaxy. It is a technique which cannot grow very small layers, very thin layers, but it can grow very thick layers. So basically, it is a hot wall reactor. You see here, this is the real reactor. This is the hot wall chamber. And this is the loading chamber. From here, you are loading the wafer. And what you are doing here is actually, you are generating metal chlorides as 3 group sources. So for example, gallium chloride and indium chloride. So you pass HCl through gallium and indium, you generate in situ. And you have hydrides like arsine and phosphine as 5 group sources. And then they all come and react on the substrate, and you can grow the indium, gallium, arsenide, phosphide, for example. Now, this technology has a very high growth rate, and also it can grow very selectively at certain places where the layer is, where the wafer is masked. It will not grow on the masked region, but it will grow only on the open area. Okay, so, and these are the two things which we use actually. So we cannot compete with the MBE or MOVPE to grow nanostructures or quantum wells, but we can grow very thick layers, and that is where we exploit this technology for fabricating very advanced devices. Of course, we cannot make these advanced devices only by VPE. We need the basic source, the basic structures grown by MOVPE and MBE. So why it is an equilibrium process? You say it is an equilibrium process, I said, but how it is, why it has a high growth rate? Because in equilibrium process, you have this is a thermodynamic driving force, and here is the growth rate you can call. And the equilibrium process is a kind of, it grows, it straight up, whereas the diffusion process, it will go up when you increase the delta mu, and it will planarize, kind of stop here. Whereas it will keep on continuing growing because it is an input control process. Okay. Okay, let me go to some of the examples of the devices which we have fabricated. And first of all, I will talk about light sources on silicon. The need for indium phosphide on silicon for photonic integration. We have silicon is an excellent material, but silicon dioxide renders silicon as an excellent material for electronics. Without silicon dioxide, silicon cannot do much. And the silicon dioxide also renders silicon as an excellent waveguide. So we have a lot of things which are available on silicon, but there is one thing which is missing. The detectors and modulators are also feasible with silicon and germanium. But light sources for silicon photonics, if you want to have light sources on the integrated circuits, we do not have light sources on silicon. We can make only from silicon. So indium phosphide on silicon is a solution, or 3-5 materials on silicon is a solution, because 3-5 materials can produce light. It is, most of the 3-5 materials are direct bandgap material, and silicon is an indirect bandgap material. So you may refer to some of the two recent books which we have edited very recently on silicon photonics if you want to know more. So light sources on silicon which are necessary. And also multi-junction solar cell. You can also try to grow 3-5s on silicon so that you can achieve very high efficiency on a very low cost wafer. Okay. And these are something which people are aiming at. We are also working on it. And light sources on silicon is for silicon photonics. But also you can use for ultra-fast electronics on silicon by integrating 3-5 on silicon. So there are different approaches for integration of 3-5s on silicon. One is the bonding approach. There are several approaches in bonding: molecular, adhesive, transfer printing, and epitaxial methods: direct growth of indium phosphide, indium gallium arsenide phosphide on silicon, thermal cycle growth, and growth of dilute nitrides and borides, lattice match to silicon, and epitaxial lateral overgrowth. I mean, people are taking several approaches, all these approaches, and we are trying to do this integration through ELOG, what we call ELOG, epitaxial lateral overgrowth. So what is it? Actually, you have a substrate, silicon substrate, and you put some very bad quality of indium phosphide on silicon. It contains a lot of defects. The lines are the defects. And then you put a mask, a dielectric mask, make an opening, and then you grow in the reactor. What will happen is the layer will grow only selectively in the opening, and when it reaches the height of the brim of the mask, it will try to grow laterally. That is why it is called epitaxial lateral overgrowth. And the good thing about this is, in the opening, you will propagate these defects, but they will not propagate above the mask. Okay, so this means the layer which you are growing away from the opening, they will be of good quality, and you'll be able to make use of it for making devices. And this was the very first layer, India phosphide ELOG layer we have grown on silicon. So in fact, if you look at this is the TEM picture of the India phosphide grown on silicon dioxide, I mean on the dielectric mask. Actually, the layer really adheres to the silicon dioxide interface, I mean surface. So it is a very, very, very clean material. So how can we use this for integration for silicon photonics? So if we use, for example, here is the seed layer, and you have the opening. Now you have two openings, adjacent side, adjacent openings. And what you are doing is, instead of depositing just silicon dioxide, you can make use of the silicon dioxide mask as a silicon waveguide. Instead of silicon dioxide mask, you can make use of it as a silicon waveguide. And the growth does not distinguish between silicon dioxide or the waveguide structure. It is completely immune, and it will grow only selectively in the opening. So you can grow, for example, your India phosphide, and you can coalesce, and afterwards you can grow the quantum well structure on the top. So the beauty is, if you do this, if you succeed this, you can couple the light into the silicon waveguide, and that way you can have the integrated device on silicon. And this is one way of achieving light sources on silicon and use the silicon waveguide for silicon photonics. And this is actually the simulation. So this has been demonstrated actually by bonding techniques, and not much has been done on the epitaxial side for integration. And actually we patented this concept. So I just want to show you some of the high quality material which we have grown. So this is the high quality indium gallium arsenide phosphide multi-quantum well grown on ELOG India phosphide on silicon. And here is the photoluminescence spectrum for the reference, and here is for the multi-quantum well on India phosphide on silicon. So it actually, we get almost 80 to 90% of the intensity with respect to the reference sample. But unfortunately, we are not able to make a device on that for several reasons. For example, we tried to make micro disc lasers, and we got very, very strong spontaneous emission, and we have not obtained the laser yet. And we tried to make recently, we tried to make lasers, but the laser did not work. On the other hand, we tried to see if it can work as an LED, and in fact, it worked. So this is the structure which we have grown. Actually, these structures were grown. We grew only ELOG India phosphide on silicon, and here these structures were grown by MBE, and these were processed as LED. This is a top view. This is a ring contact, so the light will come out from the center. Okay, so this is a ring contact here. And this is the room temperature electroluminescence of multi-quantum well on India phosphide on silicon. Actually, this we have just submitted, and it has been accepted for publication in Optical Materials Express. So we are still yet to make lasers. So this is actually a big step. At least it works as an electrically pumped device. Now, I would like to show something for solar cell applications. So I told you that we can grow the indium phosphide on silicon. If we do that, we can have, so here we have silicon. This is the size of a pizza nowadays, and it costs only $1 per 150 millimeter diameter, okay? And the size is 300 millimeter, and efficiency is 29%. And the applications are cheap and solar cell. But the 3-5 materials, it is a size, the size of the wafer is like a biscuit, and the size is 50 to 150 millimeter, and the cost is $100 per 150 millimeter. You see, this is a very huge cost, okay? But the efficiency you can obtain is 45%. So why not you combine these two? So if you combine, expected results are 2 birds in 1 bullet. So you can achieve high efficiency with low cost, because the substrate is a very high cost here, whereas the substrate is low cost here. So if you deposit, then you can deposit on a large area on a low cost substrate, you can have a rather high efficiency. So this actually we try to do with a different technique, actually kind of modified the technology with ELOG, which we called corrugated epitaxial lateral growth. So in the ELOG structure, if you remember, we have always a dielectric layer in between silicon and the material you grow. So Yanting Soon, one of my colleagues, he came up with a bright idea called corrugated lateral overgrowth. What is it? So actually, you still keep the seed layer, but you don't deposit the mask here. So you have the seed layer, you make a ridge of the seed layer, and you cover the seed layer, but make an opening only on the top. If you do that, the layer grows from the opening here, and it grows laterally. And then when it has come here, it tries to grow down and then goes and presses the substrate. So actually it is a kind of epitaxial bonding, because since our technology is completely selective, there is no nucleation here. So everything is coming from here, and the growth will proceed downwards, and it will have an interface with silicon. So in that way, you can have some 3-5 material directly on silicon, just like bonding. So we have demonstrated, and this is the interface between silicon, and here is the TEM, the X-ray diffraction picture, and we can see the signature of both silicon and indium phosphide. And the electrical characteristics also show it as a rather good interface. And again, it has been patented. And so we wanted to demonstrate whether this works even as a PN diode. And we made this kind of structure. We allowed to coalesce. And then you see here, this is the PL mapping of this structure. This is a seed, and the CE-log layer, what we call CE-log layer here, which is in connection with the silicon at the interface. It is the best quality. This is the quality. The intensity is the highest quality here, and we have the highest quality here. And of course, it is very mediocre results, but this is a proof of concept. At least we can show that the diode works. This is the photocurrent, and here is the dot current, even though the short circuit current density and the open circuit voltage are not really fantastic. But still, it is a proof of concept that these things work. Okay, then I will go to the buried heterostructure quantum cascade lasers. Let me see the time. So there I will try to show some examples where we have contributed for ridge lasers, microstripe lasers, photonic crystal lasers. Why buried heterostructure lasers? Because it allows efficient heat dissipation. If you don't have this kind of structures, all the heat which is generated in the device, it will not dissipate, it will only go through the device and it will mess up, it will destroy the laser structure at the operation. So this will give high output power and room temperature and CW operation and high beam quality, high wall plug efficiency. Well, this is something which we have been working on this for some time. When we worked on telecom lasers, so we demonstrated these buried heterostructure lasers, also very useful for high-speed lasers, high-speed operation, high-speed modulation, which is used in data communication. So when you are just, how do you say, you are not patient when you download your film, and that's because the lasers probably which are used are not fast enough or somewhere or something else. The lasers are fast, but something else is limiting. And we need fast enough lasers to transfer data. And so at the time, this is from 97, we demonstrated 30 gigahertz bandwidth. So this is the buried heterostructure laser. You have the laser structure and you are burying the laser structure in the semi-insulating indium phosphide here. And so this was done when I had a little bit more hair, but not much now. So, and we try to implement the same thing for QCLs, quantum cascade lasers. Quantum cascade lasers, yeah, I mean, they are very, you can fabricate from 3.5 to 24 micrometer using the same material systems. And it has a lot of application in the sensing area. It covers most of the gases, poisonous gases, and you can sense them. And so just for very, very briefly, I would tell you the difference between the regular interband lasers and inter-subband lasers, which is the quantum cascade lasers. So the interband laser, actually you have the communication between the conduction band and the valence band, so the electron-hole recombination across the forbidden band gap. Whereas in the inter-subband laser, you have the communication within the well, okay? So you don't have p-n junction, you have only one layer, n-type. So transition between levels created by quantum confinement within the conduction band or the valence band, so far that has not been demonstrated. So what happens is, so when you are biasing and injecting, each electron, when it falls down to the lower level, it emits one electron and it goes to the next level, next package, and then goes down here again, emits one more photon. So that way, depending upon the number of stacks available, number of steps available, one electron will emit n number of photons depending upon the number of stacks you have. So that is the beauty of this. And what is interesting is actually, this is a kind of, this is the buried heterostructure laser, how we fabricate. We have the quantum cascade laser active region, and we have the cladding, and you etch down, and then you are doing regrowth of indium phosphide, iron doped indium phosphide. Now, the particularity with QCLs is respect to telecom lasers is the QCL structure itself is very, very thick, 7 to 15 micrometer. So if you etch down and try to regrow this material, it is very difficult with other techniques. And that is where our technology comes, VPE comes. So the basic structures are made by MBE or nowadays even MOVPE, but these regrown structures are done by VPE. And QCL also needs tens of volts and amperes to pump. So in contrast to telecom lasers. So this means the heat dissipation must be facilitated even more. So these are some examples of the structures which we have regrown. So very, very clean. This is active region, and you see this is the indium phosphide, iron doped indium phosphide. And this is a 5.5 micrometer laser, which was provided by Professor Capozzo, so one of the inventors of QCL. And we could grow in a very, very short time. Regrowth time is only 13 minutes. If you have to do this in VPE, MOVPE, it might take hours. So you see the beauty of this technique. That is why we are using where it is strong. And not only wet-etched mesas, but also you can use ridge, which are etched by dry etching, and you can do also regrowth without much of problem. And this is 8 micrometer deep, and it was regrown in 12 minutes. And this is just a collection of several runs we made. This is the type of ridges we have made. And this is a kind of a very simple, this is a kind of a trench structure. So depending upon this, you can have the regrowth time depending upon the etched ridge depth. Depending upon the depth, you have the timing is, so you have to, and you see even to grow really 14 micrometer deep, regrow 14 micrometer deep trenches, you need only 35 to 40 minutes. So this is a dream for MOVP, which cannot be really easily done. And these are some of the results of the ridge lasers. So we could go up to the maximum output power. We could go up to about 2.4 watt, and the wall plug efficiency around 8. So these are all really very, very, very good results. Well, we can also make regrowth not only on straight ridges, but also on the curved ridges, like arrayed waveguide gratings. Okay, so complex structures like arrayed waveguide structures, which this we have demonstrated in an earlier some kind of telecom applications. Optical arbitrary waveform generation, and this was a project funded by DARPA, and this is actually this picture which was published on Compound Semiconductor cover page. It comes from our reactor, actually, this picture. So, well, whether this can be applied to buried Y junction and tree arrays of QCL, and this we have demonstrated. Yes, indeed, it can be. And so this we have demonstrated for this kind of, you see here, for the straight ones, here are the regrown profile. And here at the junction here, this kind of junction, these are the regrowth profile. And these are the results. Okay, there are other types of lasers also in the micro, not only ridge lasers, but also microstripe lasers. What are microstripe lasers? Actually, you have the one ridge, but it divided into small stripes. And this actually, by simulation, they found out it has a better heat dissipation and better monomode emission and larger effective width. So the width you are increasing, but the stripes are actually small. And so you can get high power devices. And this is how they look like. This is before regrowth. You see here, and these are very, very small openings. And it clearly, you see the very, very clean growth And you see here, this is the whole structure, whole wafer here, almost, I mean, a large area. And it is growing very selectively, and it's really very, very nice. And this is a same picture and the electroluminescence of the processed chip. For example, here, the electroluminescence of 8 stripe devices. And some of the device results. You see, when I told you that it can go up to several tens of volts, so you have 15 volts it can go, and it can the pumping the current is actually 3 amperes, but these are all not at all the amount, the magnitude in the telecom lasers. Okay, then I will show you quickly photonic crystal lasers. Again, it is why buried heterostructure photonic crystal quantum cascade lasers. It's a tight optical confinement and ultra high cavity Q factor you can obtain, and possibly to control the emitted mode pattern and beam shape. And it is also suitable for miniaturized and on-chip integration of QCL lasers. So you can obtain surface emission. And this is what we have done and we have demonstrated. Of course, this we have collaborated with the group of Professor Jerome Feist, actually one of the inventors of QCL at ETH now. They invented while he was in the labs. And this is the cartoon, and here is the cross section of the photonic crystal structure. So here is the active layer, and here is the regrown India phosphide, iron doped India phosphide. You see, these are all very, very small structures. So we can grow on very big structures, but also we can grow on very, very small structures. And we could obtain 5-watt surface emitting power. Of course, it is not at room, of course, it is a room temperature, but not continuous wave operation. You can see here, it goes up to 5-watt. And very recently, there is a lot of interest for free space optical communication. So people are looking at these. QCLs are interesting because you can have in the region 8 to 11, for example, it is not absorbed by air or water and the humidity in the air. So people are looking at this range. And here, actually, we tried with our lasers, which we fabricated in collaboration with our people from France. And we could demonstrate, actually, up to 3 gigabit per second line rates. And this is the transmission experiments. Of course, I'm not a specialist in these kind of transmission experiments, but what I'm trying to say is, we are working on these lasers, which can be used for free space communication. So actually, we are working on a European project right now and concentrating on 9 micrometer lasers for free space optical communication. So finally, I would like to show you an example of a completely different structure, which is also very difficult to grow by other techniques. What I call orientation patterned gallium phosphide for quasi-phase matching. Now, non-linear semiconductors, and this is the figure of merit, but what is the need for that? The devices for high brightness, entangled photons. Now we are talking about quantum communication. We need high brightness entangled photons for quantum information technology. And of course, there are certain sources available, but they are not bright enough. So people have come up with the idea by using nonlinear semiconductors via quasi-phase matching of symmetry polar semiconductors. And these are some of the semiconductors, operation wavelength, and the figure of merit. And you see here, there are some devices, actually, these are all a bit difficult to grow by our technique. I don't think people have demonstrated very thick layers, but here people have demonstrated very thick layers, and we are working on gallium phosphide, orientation phosphide, gallium phosphide. And quasi-matching principle, actually you invert the structure, and the chi2, this is, if this is plus, this is minus, this is plus, this is minus, this is plus, and try to grow very thick layers, okay? And then when you pump with a laser, you will have 3 emitter wavelengths, idler and signal, and you can optimize the periodicity and the pumping wavelength, and you can obtain the entangled photons from the photons which they come out. And this is the top view of this structure. And we try to grow, we have knotted, so this is the cross-section view, which is of the structure. So you have in this direction, you have 0, 0, -1 direction here, whereas here is 0, 0, 1 direction. Okay, so it is inverted. And this is the latest results we have. They are not really fantastic enough, but we have at least achieved some kind of boundary separation. So when you are trying to grow like this, so it happens that you do not get the boundary separation between these. If you don't have the boundary separation, it will not be useful. So at least we have achieved the boundary separation, but they are not thick enough. We need to grow at least to 500 micrometer, and this is only around 40 to 50 micrometer, and they are not at vertical enough. So we are optimizing this growth, and we are working on this. Okay, I think that's all I wanted to say. So I just want to summarize. HVP is a near equilibrium process. It has a high growth rate and high selectivity, and is suitably exploited for 3-5 silicon integration. And I've shown you that in multi-quantum well laser structure with electroluminescence demonstrated, and P-N junction silicon indium phosphide photodiode demonstrated, and buried heterostructure, different types of buried heterostructure QCLs for high beam quality. So the future is actually we have to demonstrate long range free space communication with the 9 micrometer QCL, which is we are working on, and also establish a good process so that we can reach this orientation pattern gallium phosphide for entangled photons. So I would like to acknowledge all my coworkers, students, and also I have had the privilege of working with great people all around the world, for different types of topics. QCL, the people really who invented QCL, it's really amazing. And also on integrate silicon photonics with John Bowers, and also people at Tyndall, Francois Lelarge, and all my technologies. And here, the orientation pattern substrates, Bruno Gerard, Arnaud Brissard from Thales Research Technologies, France. So with that, I would like to thank you all for your attention. So thank you very much.
Thank you very much, sir, for a wonderful talk, wonderful and informative talk. So there are a few questions has been raised by the participants, and with the constraint of time, we can ask a couple of questions. I think 1 or 2 questions we can ask. The first question is, for growth of aluminum gallium nitride film for UV LEDs, which one is better technique, SVPE or molecular beam epitaxy technique?
Aluminum gallium nitride?
Yeah.
The aluminum gallium nitride is a bit difficult to grow by VPE, even though there was a company called TDI, they started some time ago. I do not know whether they really exist. So for very thick layers, I think recently the NREL, National Research Energy Laboratory, they have demonstrated they can grow aluminum containing materials by VPE, but you have to have the sources, you have to have a special construction. So to answer to the question, today it is mostly by MOVPE, but people are looking at using even VPE for growing aluminum gallium nitride because it is a very, very cheap technique.
Okay. Thank you, sir. One more question is, in the quantum cascade laser you have shown, how is the monochromatic light emission achieved as the quantum well fabricated in cascade can have variability in thickness or dimensions?
Sorry, I did not hear properly. How is
Okay.
the?
In the quantum cascade laser you have shown,
Yeah.
how is the monochromatic light emission achieved as the quantum well fabricated in cascade can have variability in thickness or dimensions?
No, you have to optimize the whole structure. The whole structure you can simulate the quantum well structures, and the cascading you have to simulate it. It is the same. You have to have the same wavelength. Okay, so you have to really control the thickness. That is where the growth technique comes, which we cannot do in VPE, but it can be only done by MBE. So it is accurate control of the structure, and that is really people have to really work on the control of the thickness and the composition of each layer.
Thank you, sir. One more question is, what is the thickness of silicon wafer before lithography and after lithography in HVPE?
Oh, the standard thickness which we don't have anything special thickness for wafer.
Okay.
You can.
Okay, thank you so much, sir. Actually, we are running out of time, so we have to conclude and we have to go for the next session. Thank you for your nice presentations.
Thank you.
And over.
Thank you, Dr. Sebastian, sir, for the interesting talk, and thanks again for accepting our invitation. It's an honor to have you here.
It is my pleasure, madam. Thank you very much.
My pleasure.
Thank you.
Yeah, thank you, sir. Thank you.
Thank you.
Have a
Thank you
great
very
day.
much, sir.
Yeah.
Thank you.
Bye.
Bye.
Yeah. I think Dr. Mola has joined the session. Dr. Mola, maybe we can end the session and then we can rejoin back, to enable live streaming.